Hello again, YouTube. The last time I introduced the library of code libesoup and we created a bare bones project. So this time I've got my logic probe here, the Sealy Logic 8-port 8-channel logic probe, and I'm just going to use it to demonstrate hardware timers, which is one of the modules or functionality of libesoup. So if I just pull in the latest, because I work on a different machine, and so that's the latest and greatest. And if we pull in that open that bare bones project that we had the last time, we will have, basically I've added a header file because I put it into the repository, and basically we had a main that did nothing. The only thing it did was initialize the library of code, and we had a configuration, and the only thing we had to do was specify a clock frequency for that we want the system to run at. So I'm going to define hardware timers. So that switch macro, the definition of that is going to pull in the hardware timer functionality. Because I created this as a bare bones project the last time, I didn't include all the library of code, but I've obviously got I'm very surprised that it's got that, because it doesn't have hardware timers. MPLabX can get kind of confused. Oh, sorry, I've spelled timers wrong. That's more like it. Now the call to initialize the library is trying to call this function to initialize the hardware timers, which we don't have. So if we just add a folder, if we add that timers folder to the build and build again, we still have a problem with hardware timers not being included in the build. You actually have to close the project. Once you've added the folder, you've actually got to close the project, open the project, and then it should build. It's just something to keep a note of, because you can be there trying to find why it's not building because you've got the code included but it fails to build. Yeah, close the project, open the project and start again. So after including the switch into our configuration file, we'll include delay.h and hardware timers.h. So delay is synchronous in that it won't return, it will just spin on a for loop like we did in one of our early examples. So if I call delay, if you look at the definition for it, it takes that's the actual implementation. It takes units and a duration, and the duration is a UN16, because negative durations don't make an awful lot of sense. So the units, we've got a type here: microseconds, milliseconds, seconds, minutes, hours. Now Minutes and hours are only in there for completeness. And the cinnamon bun has a hardware clock, a real-time clock, so minutes and hours will get to at a later date. But don't be putting minutes and hours into a call to delay or hardware timers, because you'll get an error on that. Return a negative error on the call. So we'll just set it to milliseconds. So we want to delay. Actually, let's delay for 2 seconds. And as I say, that's a synchronous function, so it won't return, but it does. When it does return, it will return an error message. So I'm really bad at checking the return from delay, but you should check the return from delay. And since we are connected to the board, we have a LED on. We've got a LED on D0, so we could actually initialize that LED to be an off, and if there's an error, we'll illuminate the LED and just keep an eye on that error condition. So that's a delay. We've got there's no messing with special function registers, setting up timers and all the rest of it. We've set in our library of code, we've set a clock frequency that we want, and then the code will actually work out what it needs to do to create our timer. So we've got a 2-second timer, it'll do the rest. So if we want to do a hardware timer, we would call hardware timer start. And I'll just pull that from this include file. So that returns, if I just paste that there, that returns a timer ID, but that timer ID is also the same as a return code. It's an int16. So we've got it will return, if it's less than 0, that's an error code. So we've got another error. If we had an else on that, we could say a timer ID is that return code. So if it's 0 or positive, then we can say that the timer ID, if we wanted to cancel that timer in future. But since we're not going to cancel a timer, we'll just check on the return code, and that's us. And that function, hardware timer start, just takes a pointer to this request, timer request structure. So all we have to do is call hardware timer start with the address of our request structure. And to fill it in, there's a few things, there's 5 things, but let's start with, we've already seen units. So we had microseconds, milliseconds, we'll just go for milliseconds. So on a millisecond timer, and the duration, self-explanatory, will go 100 milliseconds. Now the type, timer type, there's only 2 timer types. If I go to the definition of that structure and timer type, there's a single shot, which is just do it once and that's the end of it, and a repeat, as the name suggests, does it constantly over and over again. I'll show you that in a minute, but we'll do a single shot. So we want a single shot timer. Sorry. We want, the next thing we want is an expiry function. I'm going to call it expiry expfn, but the definition for that is just above so we'll implement it here. But this expiry function, it's a point in the structure, it's a pointer to a function. So if we just get rid of that, the pointer, so we have a void that accepts as parameters a timer ID and this union. And that union is actually included in this request structure as data. And it's a union of either an integer, a 16-bit unsigned integer, or a pointer, which in this architecture is 16 bits as well. So in both cases you can either interpret it as you're getting 16 bits, either interpret it as an unsigned integer or as a pointer. And that's a request structure, the 5 elements of it. So once the timer expires, this data, which we're specifying as 0, is going to be passed into this expiry function, which we've defined up above. It does nothing at the minute. And that's the simple request a timer. And it's actually requesting a hardware timer. Now, the number of hardware timers there are in the system, I can request multiple timers, but there are limitations. So eventually, if you did a for loop and tried to start a number of timers, eventually there's only so many timers on the actual device, this DSPIC33, so it'll eventually return an error if there's too many being used. So what do we do with this timer? So we'll, just for the sake of argument, we'll take because I've got my logic analyzer plugged into D3, we'll initialize D3 as an output pin, set it to 0, and then just before this timer request, we'll set it to 1. And in the expiry function, we'll set it back to 0. So all this is going to mean is we're going to have a pulse, a high pulse, for hopefully 100 milliseconds. So if I program that, and go to our logic analyzer, I'll set that 5% after that, but sorry, I'm all over the place. That's the one I'm looking for. Disable all. I've only got D0, and that's actually on D3 of the cinnamon bun, and will trigger on a high pulse. Maybe go up to 50 kilohertz, and I should only need a couple of seconds of samples. I'll switch it off. Sorry, I don't know what it's, switch the unit off, so I don't know what it's triggering on. So there's our little pulse. So if I bring up the, actually if I zoom in, to get as accurate as possible, and we pull up a cursor, and there's our 100 milliseconds of a pulse. So we could change that to, if I changed that data structure, I could say, could change that to 200, and let's go for microseconds. So if I re-trigger on that, sorry, I'm not running. Oh, one of the things I didn't do, I meant to set this to be, we'll have a 200 microsecond, but we'll do a repeating timer. And if we're going to do a repeating timer, then we're going to have to just swap just toggle the, oh sorry, got the wrong pin. We want to toggle D3. And just to check, 200 microseconds and repeat, and the loop, the while loop, the main loop of our code is again going to do nothing. So if I, all those pulses are from programming, so if I start again, you can actually see that was the pulses. Hold on a minute. So if I just stop and zoom in, there's our a repeating timer, and I might not be too accurate with my cursor. I'll zoom in again, but that is about, and I've got 201 microseconds there, which is about as accurate as I'm going to get it given the samples. Sampling at 50 kilohertz, but it's close enough. Yeah, 200 microseconds, and that's just hardware timers. There's no messing with special function registers. If you actually look at the code in, there is a project in the an example project, hardware timers, and it has a number of hash ifs in the code, because this code will run on the advantage of creating an API is that you have an API for starting a timer. You don't mess with the special function registers. You just call that, and the actual library of code does all the heavy lifting. And because of my development, of course, over the course of my development, I have played about with, if I just move this to one side, I've played about in the past with a PIC 18 and a PIC 24. So this project can be built for, you're using the same high level code, so you're creating, always calling this, I'd probably call, I might actually call both, because this is as well as it being an example project, it's also a test project. So I test, I run this if I want to test like single shots and repeats. One of the things about the PIC 18F is it's not, one of the reasons I moved away with it from it, it's not really ideally suited to C programming. So it can't handle recursive function calls. So this repeat isn't possible in a PIC 18. I didn't like the compiler, which is probably down to, I didn't like the actual PIC 18 isn't optimized for C code. It's really for assembly, I suppose. So there was various things about the compiler I didn't like, so I moved to a PIC 24 and then eventually moved to PIC 33. And if I was doing it again, I'd use a completely different microcontroller. But yeah, this call to start, the request structure is exactly the same. So you're filling out the units and the duration, you fill out the type of timer and an expiry function and the data you're passing to that expiry function. And then in either case, whether you're compiling for the PIC 18, PIC 24 or DS PIC 33, you're always calling the same start a timer and let the library of code sort that out. So depending on the clock frequency, depending on the platform you're running, and some of these, that I can't remember the details, but the PIC 18 probably only has 3 or 4 hardware timers, whereas the DS PIC 33 has more timers, more hardware timers in the silicon. And that's just, yeah, that's an introduction to hardware timers in the libesoup. That hardware timers project is in the Git repository, so you can look at that as is. I won't commit this bare bones. I've just edited bare bones to add hardware timers, but I won't actually commit that back into the repository. That just shows you how easy it is to just add a switch into the configuration file. If I maximize this, so you just say I want to include hardware timers in the build, so the project will build with hardware timers, and I can call delay and start a hardware timer from that with very simple calls to an API. So I leave it there. Thanks a million for watching, and I'll see you again soon.